Hello, and welcome to my presentation. Today I will be discussing Conway's Game of Life in Cellular Automata. Well, what is it? Conway's Game of Life, or more simply, life, is a non-elementary, two-dimensional cellular automata. It consists of a grid of cells known as the life field, which occupy one of two states, dead or alive. Each cell on the life field adheres to a rule which determines whether the cell will be dead or alive in the next time step. The name is kind of a misnomer, as it is not a game in the conventional sense. The game is a dynamic system, and the only interaction a player has is setting up the initial configuration. Nonetheless, the game provides an endless amount of variety and entertainment. In order to define the rules of life, we must first establish some terminology. The rules of life are built upon the definition of a neighborhood. The neighborhood of a cell is the set of cells adjacent to it. As a result, the definition of a neighborhood depends on the definition of adjacency. The initial construction of life is with the Moore neighborhood, the union of the orthogonal and diagonal cells. A common variant in life is using the von Neumann neighborhood instead, as it leads to very different dynamics. Altering the definition of the game is a common pursuit by those who research life, as life is a dynamic system, and as such we investigate them by making small changes and observing the result. Other modifications to the neighborhood definition could be the depth, or how far out from the cell of interest we consider adjacent. The rules of the game are very simple. Any live cell with 2 to 3 living neighbors survives for the next generation. Any dead cell with 3 live neighbors becomes a live cell. All other live cells die in the next generation. Similarly, all other dead cells remain dead. The rules were originally formulated with the following 4 scenarios in mind. When Conway designed life, he was attempting to emulate population dynamics. If a cell has too few neighbors, it dies of loneliness or falls prey to local predators. At the other extreme, if a cell has too many neighbors, it dies from overpopulation. Any cell with more than 3 adjacent cells becomes alive, and any cell with exactly 2 neighbors remains alive. Through countless hours of exploration of Conway's game, fans of his creation found fascinating initial conditions. Interesting initial conditions are referred to as patterns, and the community has defined various categories for them to fall into. The categories I will touch upon in this presentation are the essentials: still lives, oscillators, guns, gliders, and Methuselahs. Still lives are patterns that do not change as generations progress. They are static structures. Still lives are classified into 2 subgroups: pseudo-still lives and strict still lives. The pattern on the left is a pseudo-still life. This is because it is composed of 2 still lives that do not interact with each other. On the right-hand side, this pattern cannot be broken up into smaller still life patterns, so it is a strict still life. Here is a variety of low period oscillators. This diagram groups oscillators of the same period together. You can see how oscillators of the same period have very different sizes. Spaceships are patterns that are similar to oscillators. Just like an oscillator, their structure cycles through a fixed set of states. However, a spaceship's root position will change when it cycles through a period. Spaceships are classified by three main attributes: size, speed, and period. The speed of a spaceship is the number of cells it traverses in its period. This is the earliest discovered spaceship, known as the glider. It travels diagonally across the life field at a speed of c/4, 1/4 the speed of light. It is one of the most studied patterns in life and can be used in fascinating ways. One remarkable usage of the glider is glider synthesis, which is the process of combining many gliders to create other life patterns. Showcased here are some simple glider synthesis formulas. Notice that these examples rely on the combination of only two gliders. More complex patterns can be generated using more gliders. Here we see the glider synthesis in action. Guns are life patterns that emit spaceships. They are similar to an oscillator, since the gun does not deviate from its fixed set of states. However, guns produce projectiles. They are categorized by three main attributes: size, period, and the number of barrels. The number of barrels of a gun is the number of spaceships that are emitted per period. This construction is one of the earliest discovered guns. It was found by Ralph William Gosper Jr. in order to prove Conway's conjecture about the existence of patterns with infinite growth. Gosper is also famous for his creation of the hash-life algorithm, which is the state-of-the-art algorithm for computing life. Here, we see the gun in action, the top portion of the animation being the gun itself, and the diagonal line of projectiles being the spaceships it shoots. Methuselahs are patterns that exhibit extreme growth and nascently appear to be unbounded, but eventually stabilize after many generations. Methuselahs are characterized by their size and lifespan. The lifespan of a Methuselah is the number of generations it takes to stabilize. This is a demonstration of the Methuselah called rabbits. We see that the initial pattern grows rapidly and sporadically as time progresses. When we fast forward, we see that it takes about 18,000 generations for the pattern to stabilize. In order to better understand the phenomena we see in life and to make changes to the system, it is important to grasp the concept of elementary cellular automata. A one-dimensional cellular automata is a row of cells instead of a grid. Like life, the cells take on one of two states at any given time. The neighborhood of a one-dimensional cellular automata is the left cell, the right cell, and itself. Since the neighborhood of a cell consists of three cells, and each cell can occupy one of two states, it is easy to see that there are 2 to the power of 3, or 8, orientations of the neighborhood. We can map each of these cases to alive or dead with an 8-bit binary string. Therefore, there are 2 to the 8, or 256 rules for an elementary one-dimensional cellular automata. Rule 22, for instance, falls into the highly structured case. Those of you with exposure to the study of fractals will recognize the emerging pattern. Rule 22 produces Sierpinski's triangle. Rule 30 would be an example of a highly chaotic rule. It is well studied because it produces complex, seemingly random patterns from simplicity. A fun fact about Rule 30 is that it is used in the math software package Mathematica to generate pseudo-random numbers. Now that I have covered elementary cellular automata, let's put life in context. Life is a non-elementary, two-dimensional cellular automata. It is non-elementary because its rules does not depend does it is non-elementary because its rule does not follow the convention laid out in the previous slides. An elementary two-dimensional cellular automata would be governed by a 2 to the 9-bit rule string, since the Moore neighborhood of a two-dimensional space has 9 cells. Furthermore, there would be 2 to the 9 possible rules. However, life is some logical composition of those elementary rules. Life can be formulated as the union of all rule strings that satisfy its conditions. While life itself is very fascinating in its own right, other cellular automata are inexplicably beautiful. Life is a starting point for the exploration of the vast field of cellular automata. I encourage you to do your own research into this area. There is so much more to be said about life, let alone cellular automata in general. The depth of substance in cellular automata is elucidated by the fact that philosophical scholars use it to argue about the concepts of free will and determinism. I'll end this presentation with a short video showcasing three-dimensional cellular automata.